uncertainty quantification from the Bayesian point of view. I want to start today. We're about halfway through now, and we've covered so many small things that details that it might be good to begin today with a possibly fairly extended look at the big picture again, to try to find the forest again and not get lost in the trees. But first I'd like to orient you to some new stuff on the course webpage. Next week, we're also going to be meeting in a non-standard place, a meeting room called Araujo, which is also on Charleston Road, a bit further up the block than where we are here today, I guess, at 1295. And so we're here on building 1220 today, and a little bit up the street from where you came in off of the 101 on the right-hand side will be building 1295 for next week. I have some new stuff for week 5 and some new data and code at the bottom of the page. First, there's a little bit of new stuff in week 4. I added part 2 of the extra notes. This is the stuff that I wrote as we talked last time, so that may help you reconstruct what we did last time. And then here in this week, I had left 22 pages of this up on the web page last time, but now I've got the whole thing there. So this is the main thing we'll be talking about today after we finish talking about MCMC in general. Today's mostly devoted to hierarchical and mixture modeling. Another name for hierarchical modeling is multi-level modeling or multi-level analysis. And I wrote a chapter on Bayesian multi-level analysis in MCMC in a book called The Handbook of Multi-Level Analysis. I have a copy of it here, but I've also made available to you here on the web page a free PDF of the entire book because the editors, Jan de Leeuw and Eric Meyer, just gave all the contributors a PDF of the whole book. This might not be quite the very final edition version that got printed, but I think it's quite close. And so you can read the first chapter to get a sense of what hierarchical modeling is about. And then you can go into my second chapter, and it will reinforce the ideas about MCMC in, I hope, a quite clear and user-friendly way, and then also reinforce the ideas about hierarchical modeling that we'll be covering today. And then there's a lot of other useful stuff in this to go into the topic of multi-level or hierarchical modeling in much more detail than we will have time to do in this course. There's an interesting piece that you might find worth reading offline. This is a book review from the New Yorker magazine a few years ago that documents some difficulties that people have in trying to use maximization of expected utility as a good way to make decisions. And so a guy a few years ago wrote a book called The Paradox of Choice. Essentially, the punchline of the book is that unlimited choice can produce genuine suffering. There are many examples. This connects with the work I showed you earlier of Kahneman and Tversky. Here's an example of the sort of thing that has been demonstrated by actually running studies on people. Having a lot of choice, in other words, having the action space be large, can actually encourage people to not act at all. Of course, not acting at all is always one of the possible actions in your action space with respect to the thing you were thinking about doing something more proactive about. And so you see here at the top of this page 92 and from the New Yorker, in a study conducted several years ago, a group of shoppers were offered free samples of 6 different jams, and people were randomized into 2 groups. One group was offered free samples of 6 jams, and the other group was offered free samples of 24 jams, which included the 6 in the other experiment plus 18 other ones. And shoppers who were offered the 6 jams were much more likely to buy a jam than the ones who were offered 24. They were, in effect, they were very badly daunted by the prospect of having so many things to choose from, and they just threw up their hands, either literally or mentally, and just walked away. That happens over and over again, it turns out. As the writer of this book review says, this result seems irrational. Surely you're more apt to find something you like from a range that's 4 times as large, but it can be replicated in a variety of contexts. Students who are offered 6 topics they can write about for extra credit are more likely to write the extra credit paper than students who are offered 30 topics. And again, the list of 30 topics includes the 6. And yet, when they have a chance to choose one of the 30 topics to write a paper for extra credit, or choose one of the 6 topics to write a paper for extra credit, by a quite large margin, the group that was only offered 6 things to choose from is much more likely to take up that offer and write the extra credit paper. And it's a very strange thing if you think about it that way, because obviously wouldn't you want as much choice as you could have. Anyway, you can read through that. I think you'll find it kind of interesting. In order to accommodate those of you who do not dwell in the blessed and cursed world of Mr. Bill Gates in your daily work, I have been forced into that realm by doing a lot of applied work with people who work only in that realm. So I showed you last week a package called WinBugs, which only works under Windows. Since we last met, I have mastered a variant on WinBugs called JAGS, which stands for Just Another Gibbs Sampler. It was written by a guy called Martin Plummer, who was trying to be a little self-deprecating when he calls it that. It's actually quite a nice piece of code. And he did it because, as I mentioned last week, the WinBugs people, toward the end of that, the life of the WinBugs project, showed no interest at all in porting WinBugs to other operating systems. In the very early days of Bugs, and by the way, you will agree that that's a rather strange name for a piece of computer code. It stands for Bayesian Analysis Using Gibbs Sampling, BUGS. And it's an example of David Spiegelhalter's sense of humor. In the very early days, Bugs was available only under Unix and Linux platforms. Then they were told that this was not user-friendly enough by the British analog of the NSF who were funding them, and so they decided to create a Windows version of this thing, and then they called that WinBugs, of course. And they developed that through a number of releases, and then eventually stopped developing it when they felt that it was pretty stable. But they had no interest in porting that code to Mac OS X or other platforms, and there's a lot of Mac users in the room. So Martin Plummer decided on his own to do a service for all of us that has the following form. He takes the exact same structure of the model and the data and the initial values files that I showed you in WinBugs, and he has rewritten things so that you can feed all those things into R, to a package he's written called RJAGS, and then you're up and running. And so my intention today is to show you, those of you who would like to use this instead in your own computing, I'll show you how to use RJAGS on the same example I showed you last week from WinBug's point of view, the NB10 modeling using the T sampling distribution. And from that point on in the course, I'm going to continue to show you MCMC work in WinBugs, but you now will, at the end of today, or at the end of this morning, you will know in a very explicit way, because I wrote out a long document showing you how to do this, you will know exactly how to take my WinBugs code and easily translate it into the world of RJAGS and run the stuff yourself on your Mac. So there is PDF documentation for the RJAGS package in R. There's a user manual for JAGS. Martin Plummer is not the most user-friendly of guys when it comes to showing you how to use his software. And even though I'm quite experienced in MCMC and even more than one package for using MCMC, it took me a while to make sure that I indeed understood how to get the thing running. But I did succeed in that, and so we'll see that today as we go forward. And then I have some handwritten notes and some extra notes, which are also handwritten notes to supplement the work that we'll be doing today. The top of the web page says that the videos are only available for the first 3 days of the class. That's false. I need to change that. The videos for the first 4 days of the class are available down here toward the bottom. And then we have a lot of new code. After we get done with the big picture, and that brings us back to the MCMC work we were doing last time, I'll segue into this document here, which is how to MCMC sample with RJAGs. Also, I owe you an example about those of you who like to look at the world from a graphical modeling point of view. I've written out quite explicitly instructions for how to construct a model in WinBugs using the so-called doodlebugs option, where you can actually create the model as a graph rather than as a piece of algebraic code that defines the model. And I was wrong, as it turns out, in what I said last week. If you already have the model algebraically, there's no button to press inside WinBugs that will generate the graph for you, but they do have a button that goes the other way around. So you can build the graph using their graphical modeling interface, DoodleBugs, and then press a button and it will generate the algebraic code from the graph. So that direction is available. So we looked at the MB10 case study. There's a few more files there that we may look at today. And then for hierarchical modeling, I have a whole bunch of case studies. We're going to do a simple one first, a meta-analysis of some randomized controlled trials to see whether aspirin is useful to keep people who've already had a heart attack alive. A slightly more complicated hierarchical model involving a study of the question, does the following question, do the expectations that teachers have about their students actually do those expectations affect the performance of the students in class? In other words, if a teacher thinks that a student is particularly bright for some reason, possibly not even knowing the student that well, will that student end up having better performance on standardized tests than if the teacher thinks a student is particularly dull, for example? And the answer, unfortunately, turns out to be yes. There's quite a strong teacher expectancy effect. And of course, that's good for you if you're one of those people that the teacher thinks is smart, and not good at all for you if you're one of those people that the teacher thinks is dumb. So that's that story. And then our longest case study, involving our most complicated model to date, will involve a randomized controlled trial, quite a bit like the AB experiments that are done here in the Valley, but this is in the context of a medical trial to examine the effectiveness of something I actually showed you the very first day. Oops, that's not what I wanted to do. Back in week 1, the very first lecture notes, all those weeks ago, the very first example I gave was this data set that we're now going to analyze. A randomized controlled trial of an intervention called in-home geriatric assessment, which is a way to try to help people who are elderly and living in their own homes avoid unnecessary institutionalization. So we'll look at the data from that study today from the point of view of hierarchical modeling. So there's a bunch of data down there for that, various files and data. And then if we have time, this is our most complicated model of all. The data set I analyzed as my example data set in the book chapter in the Handbook of Multi-Level Analysis involves quite a complicated hierarchical model. And if there's time and interest, we can get into that either this time or early next time. So that's what's new on the course web page. And let's switch over now and spend a bit of time trying to get the forest back into focus. From the 5 weeks or so we've been, I guess this is the beginning of the 5th week, so we've been at this for a total of something like 25 hours so far, almost. And so easy to get to the point where we lose sight of the big picture. So I've written out a couple pages of big picture stuff already here, just waiting for things to start this morning, and I'll write out a few more pages as we go along. The reason we're here is that we're trying to figure out how to do a better job of quantifying our uncertainty about something that's not completely known to us than we knew before we started the course. So this is a course about uncertainty quantification. As I mentioned at the beginning, statistics for me, statistics is the study of uncertainty, how to measure it well, and how to make good choices in the face of it. And so we will talk periodically about Bayesian decision theory because it turns out to be a valuable tool to help you figure out how to draw good inferences and make good predictions. I won't be dwelling on Bayesian decision theory in its own right that much this course, I don't think, until perhaps the very end, if there's interest. But we do four things basically as statisticians on a regular basis. We do description of data sets without attempting to generalize outward from those data sets. We do inference, which is a process of trying to generalize outward. You have a data stream, a piece of a data stream, and you are trying to draw inference about the underlying mechanism that generated the data stream. Or in more standard statistical language, you view your data as like a random sample from a population, and you want to say something about what was happening back in the population. The third thing that we often do is prediction of future data values, which could be thought of as a special case of inference, but in fact it's better to keep it separate because the mechanism is different for actually doing the calculations. And then the fourth thing is decision theory, actually making choices in the face of uncertainty. And so looking now at the document camera, we notice that we have in a problem involving uncertainty, we have three basic ingredients that we bring to the table. You start by identifying something unknown and of interest to you. I'm going to call that something theta. In practice, theta could be practically anything, but if theta is an unknown of finite dimensions, it can always be written as a vector of real numbers of length k, let's say, where k is some finite integer. We will later on in the course talk a bit about unknowns that are that involve an infinite number of unknown aspects, at least conceptually, when we talk about trying to draw inferences about entire functions rather than inferences about just numbers and vectors and matrices. But for now, when we're thinking about a finite dimensional unknown, let's just think of it as a vector of real numbers of length k. And if its values don't live on the real line, for example, if the uncertainty is about whether a particular person is Protestant or Catholic or Jewish or whatever, and there aren't any natural places on the number line called Protestant and Catholic and so on, we can code those places into numbers if we want, and keep track of a little table that keeps track of the coding. So there's no loss of generality in thinking of this thing as a vector of real numbers. Then you bring to the table capital D, a data set that you judge relevant, decreasing your uncertainty about theta. And in practice, all data sets are finite in scope. We never have an infinite data set. And so without any loss of generality at all, you can think of capital D as a vector of real numbers of length little n, where little n is, again, a finite positive integer. And then the third ingredient that we always have, which is often suppressed in the notation by people who are are in a bit of a hurry in working with probability, is I'm going to call it script B, as I did earlier in the course. It's a finite collection of true-false statements, otherwise known as propositions. And all of these, so it's of the form true-false proposition B1 and B2 and ... down to and B sub K, B sub L, let's say. And the deal is that these true-false statements capture relevant background information. And because you have chosen them carefully to capture the relevant background information, you regard all of them as true. So in an experiment where people were randomized to treatment and control, one of the things in the background set is the statement, the patients in this study were randomized into two groups, treatment and control. So you have a chance with the background information to describe the data collection process, how the data came to you, and other relevant aspects of the scientific or business or a problem or whatever it is you're thinking about. So you have to bring those three things to the table. Those are inputs that you have to specify. What is that you're interested in that's unknown? What your data set is for decreasing your uncertainty, and what the background information is of the study you're working on. Yes?
What is the advantage of, I can understand making explicit that background information, but what is the advantage of encoding it as a set of true false
So Tony said he can understand the value of making explicit all of the background information that you're bringing to bear on the problem, but he asked what is the advantage of coding it in a series of true-false statements. And that advantage is that we're about to look at, to remind you of the thing that we talked about at the beginning, namely the notion of probability that dates back to that man Richard Cox, in which probability is an operator on two true-false propositions. So we're always talking about things like probability B given A. And unlike Kolmogorov's framework, where each of the things B and A are sets, which are subsets of some sample space of how things could have come out in your experiment, in the Richard Cox approach, B and A in the statement, in the expression probability B given A are true-false propositions. And so if we adopt that convention as the things that the probability operation acts upon, then we need to have where I'm about to put this script B over on the right-hand side of the conditioning bar and condition on all the true-false statements in it. So that's the reason that I'm adopting that way of coding the information. Now, as we looked at early on in the course, there are a number of ways to try to quantify uncertainty through probability. And one of the leading systems that we looked at briefly is the one from Kolmogorov, who was dyed-in-the-wool fan of the relative frequency approach to probability, in which you imagine repeating something over and over again, and you ask how often the thing of interest to you would occur in those hypothetical repetitions, and then you let the number of such repetitions go to infinity and hope that that relative frequency settles down into a single limiting value, and then that you define that to be the probability. And to make that formal, Kolmogorov's approach was to have, he didn't usually like to talk about probability of one thing given another. He was more interested in talking just about the probability of one thing. Conditional probability turns out to be, as Ed Janes noted, almost an afterthought in Kolmogorov's system. He sort of doesn't want to talk about it, but in any case, for him, the things that go inside the probability operation are sets, not true-false propositions. But I'm going to stick here with the approach that comes from Richard Cox. Also, it's the same one that was used by De Finetti. Also, it's the same one that was used by Laplace. And in that approach, the probability operator can be thought of as a function from two true-false statements to the part of the number line that lives between 0 and 1. So you give the probability operator these two true-false statements, and it's supposed to help you. You are supposed to work with it to produce a number between 0 and 1. This thing is meant to quantify your information about the truth of B, given that you regard A as true. Other people, for instance, De Finetti, think that this measures your degree of belief in the truth of B, given that you regard A as true. But I think it's more scientifically fundamental to think of probability as quantifying your information about the truth of B. And I try, this whole course I'm trying to make it clear that, from my point of view, uncertainty is a state of incomplete information about something, and so that means that statistics is information theoretic at its base. It's about information. This operation starts out, and Cox works out the basic rules of how this operator should work in order to behave sensibly, to be logically internally consistent, as we called it. And there are all the usual rules that you're used to about addition rule for or, and the product rule for and probabilities having to be between 0 and 1, all those things that you know about from Kolmogorov or somewhere else. But we find ourselves quickly wishing to make probability statements about quantities that live continuously on the real line. So let's think now of a theta, a single number theta that lives somewhere continuously on the real line. And the way we do this in the Richard Cox and Ed Janes system is to create cumulative distribution functions and densities for quantifying that uncertainty, because the statement that theta is less than or equal to some number q is a true-false statement. It's a proposition. And so I can talk about the probability that theta is less than or equal to q given some true-false statement A that I'm thinking of as true. And now I can think of that as a function of q, and I'll just call it the cumulative distribution function that quantifies my uncertainty about theta in light of the information in A. And then if it turns out that that function is continuous and differentiable in Q, then I can write that the result of taking its partial derivative with respect to Q down as a thing called lowercase p, and that plays the role of a density for a continuous quantity. Kolmogorov would think of these things as random variables, theta as a random variable, but in the Ed Janes and Richard Cox approach, theta is just something you don't know, and you're using the machinery of CDFs and densities to quantify your uncertainty about it. And so in a small abusive notation, instead of writing things with this more complicated looking notation, people write capital F of theta given A to mean the CDF for your quantifying your information about theta given A, and lowercase p of theta given A. So that's the background on probability. And that allows us to begin thinking about how we would go about updating your uncertainty about the quantity theta in light of the information in your data set D. And so at the base of things is a partition of information about theta and the presence of D partitions the total information about theta into two parts: the information about theta internal to the data set D and the information external to the data set D. And our job, if we're trying to quantify the total information about theta, is to bring both of those sources of information together. And that's done, as we know, in inference by means of Bayes' theorem. And here's how the rest of that story unfolds. So basically, to make this work, you have to specify 4 ingredients. So you started out having to specify 3 ingredients, namely what was theta, what was capital D, and what is script B. And now it turns out to reason in a sensible way about your uncertainty. There's a further specification burden on you. You have to specify 4 more ingredients. And once you've specified all those 7 things, Mr. Cox tells you something very, very relaxing and relieving. He says, having specified those 7 things, there's one and only one way to reason sensibly to draw inferences, one and only one way to reason sensibly to make predictions of future data, one and only one way to reason sensibly in making decisions in the presence of uncertainty. So you have a big specification burden on your part to line up those 7 ingredients in a way that seems reasonable to you based on the problem context. And once you've put in those 7 things, Richard Cox gives you a machine that automatically gives you the right way to do inference, the right way to do prediction, the right way to do decision. And so here are those 4 new ingredients. The first one, we have been writing P of theta given the background. And this represents your info about theta external to the data set D. And in an abuse of terminology, we've agreed to call this thing your prior information about theta, or because we're using distributions to summarize uncertainty and information, your prior distribution, DIST for short, for theta. So you have to bring that to the party. Then the second ingredient you have to bring to the party is a predictive distribution for when you're sitting around before the data has arrived and you have written out the background information, you temporarily pretend you know what theta is, and you ask yourself, what kind of data sets do I expect to see before I've actually seen any data? So this is, strictly speaking, it's a predictive distribution for your data before you've seen any of your data, conditional on the background information and pretending for the moment that you knew what theta was. Frequentists prefer to think of it as what they call a sampling distribution. They like to think of the following. If you knew what theta was, you could imagine drawing one random data set that's based upon theta, and then draw another one and another one and another one, and think about all those together. And they call that your sampling distribution because it shows what happens in repeated sampling. But from a Bayesian point of view, it's really a predictive distribution. But the crucial thing is that it represents your info about theta internal to the data set D. And in a kind of a nod to the frequentist in this, people usually call it your sampling distribution for theta, for your uncertainty about theta. Those are the two ingredients you have to specify for inference and prediction. These two are enough for inference and prediction. For decision, need to specify two more ingredients. Item 3, script A, your action space, as we agreed to call it earlier, of possible behaviors, possible choices of how to behave. And then the last ingredient is a utility function that maps from actions and the unknown theta. So A is an element, little a is an element of script A. Your utility function quantifying costs and benefits if you choose little a and the unknown equals theta. So I think of those first three ingredients as almost totally fundamental to the science of the problem. You're trying to solve a problem, and the first thing you do is you identify what's the principal thing of interest to you that's unknown. Then you marshal your data resources, and then you try to collect together all the background information that makes the relationship between theta and d meaningful by describing how the data were gathered and so on. The real heavy weight of the specification burden is these four ingredients here. You have to put one or more prior distributions on the table. You have to put one or more sampling distributions on the table. If you have only one prior and only one sampling distribution and you think that together they quantify in an accurate way what you know on the basis of the background information and the information internal and external to D, then there's one and only one way to draw inferences and predictions. And then in addition, if you want to make decisions, you have to put the action space on the table and the utility function on the table. People will usually have, as we talked about before, and much of the later part of the course is going to be devoted to this, people will usually have uncertainty about how to specify the prior and uncertainty about how to specify the sampling distribution. They will sometimes even have uncertainty about how to specify the action space. And when people make mistakes in the action space, it's generally, as you could imagine, by not including enough possibilities. For example, back in that very first case study we talked about with ELISA and testing for HIV, you might say if you had ELISA and Western blot available that the only two actions possible were either run ELISA on this blood sample or run Western blot on this blood sample. But we noticed that there was actually a smarter way to behave that we got to by enlarging the action space, namely treat them adaptively. Run ELISA on half the blood, and if ELISA says negative, conclude HIV negative, and if ELISA says positive, then run Western blot on the other half of the blood. So until we thought of that adaptive approach, we would only have been able to say which of those two actions, run ELISA or run Western blot, was better than the other. But the thing with the Bayes story is that it always normalizes to the things that you remember to think of. If your action space isn't big enough, it won't warn you that there are other actions out there that might be better. It just says, given the actions you've told me about, I can help you figure out the best one. The burden is on you to come up with the biggest possible action space. The burden is on you to express your uncertainty about the sampling distribution and the prior in a way that allows the full weight of the Bayesian mechanism, the full force of the Bayesian mechanism to capture that kind of uncertainty as well. But anyway, once we've got these ingredients, let's agree to collect them together into a little collection of four things. Namely, let's call the following things. P of theta given B, P of D given theta and B, script A, and the utility function A theta. Let's call that your model for your uncertainty about theta given D and the background information, script B. So that's where we're going to call those four things collected together your model. You could call it your statistical model. Let's just call it your model. And right now, let's put in parentheses, usually you're uncertain about theta, but you're also uncertain about how to specify your uncertainty about theta. It's a kind of second order uncertainty. You're also uncertain about how to specify your uncertainty about theta through the model. Let's call this second type of uncertainty model uncertainty. And so far, everything we've done in this class has pretended that you never have any model uncertainty. Yes, please.
Have you encountered the complaint that this formulation forces us into a false sense of knowledge about that uncertainty?
By forcing us to choose, for example, one prior choice and one sampling choice and so on? Again, for posterity, Tony's question was, have I encountered objections to this approach of the form specifying only one of these things may lead you into a position of false lack of uncertainty about them. And in fact, there used to be a school of Bayes that consisted of people who never actually worked on any real problems. There were academic Bayesians along with real in the trenches Bayesians, and some of the academic Bayesians back in the 1940s and 50s basically said things like, "My prior distribution is mine. You might have a different one. You have no right to criticize mine because my prior distribution is mine. My sampling distribution is mine, and so my posterior distribution is mine too. And there's no way that you can criticize it." And of course, that's not a very good attitude for solving real problems and keeping consulting clients happy, right? So, so in fact, that school of Bayesian story has been completely abandoned now, I think, by just about everybody except the few remaining Bayesian academics who don't actually work on real problems. Fortunately, there aren't that many of them. And the basic way we're going to approach this in the second half of the class is to first, we need to learn how to walk before we run. And so we're working on how the whole story about how to work with these four ingredients if you knew how to specify them uniquely. And then we're going to talk later about how to deal with the fact that you don't know how to specify them uniquely. Yes?
I might be able to say my uncertainty is low, medium, and high relative to my uncertainty about other stuff.
So he's saying another objection to this paradigm is that it forces you to do too much stuff. In the real problem you're working on, you may not be able to actually to be able to come up with these four ingredients and put them on the table in a sensible way. The whole structure of the Cox and Jaynes approach is, and indeed the whole Bayesian approach is, if you can come up with those four ingredients, now we know what's the best way to work with those ingredients to get a good answer. But as Tony says, maybe this is just asking too much of us fallible humans to actually be able to do this. And the principal answer to that is that it actually turns out to be not that hard to get sensible first choices of these things in any given problem. And then as soon as you've got the first choices and written them down and followed through the logic of where they lead and so on, you now are in a position to refine those first choices and make better ones. And so after a period of time, you get to a point where you discover that it wasn't an insurmountable difficulty. The principal people who claim that prior distributions, for instance, are impossible to specify, and this was something that Fisher tried to stand on quite strongly, the principal people who think that prior distributions are impossible to specify just haven't tried very hard to specify them. It turns out it's not that hard to write down densities that capture at least approximately the information you have about something unknown to you. And you might even initially not be able to pick some particular fancy parametric family to capture that uncertainty. You might just draw a sketch, roughly flat in this region from blah to blah, meaning I don't know much about any of those values in there. And I haven't shown you this, but actually Bayes' theorem can work with a sketch. It can work with a sketch for the prior and a sketch for the likelihood. I just have to digitize them, and each of them is now a function, and I multiply them pointwise using Bayes' theorem and renormalize, and you get a posterior out. So all you have to do really is sketch the prior and sketch the likelihood, and out comes the posterior that results from those two sketches. So it can even be done at that level. And people have sometimes elicited prior information from people like medical doctors just with sketches, for instance, and then quantified the sketches. Okay, so to date, we have not addressed the issue of model uncertainty, and I'm not going to do it today either. I will probably start talking about model uncertainty next time, and certainly it will occupy much of our attention for the rest of the quarter. I'll just make a little note here. We have so far pretended that this type of uncertainty does not exist. I've shown you a little bit of stuff on uncertainty in prior specification. Remember when we were working with the Poisson case study about length of stay, we were trying to be diffuse. We were trying to put down priors that expressed little information content, and we did a little sensitivity analysis in which we wrote down 5 or 6 priors like that, and we found that some of them actually had a lot more information in them than we wanted to, and the 2 or 3 other choices gave pretty much the same answer. So we've already had a little bit of discussion about uncertainty about prior specification, and we've dealt with it using sensitivity analysis. Okay, so now the payoff of this is with these star, and star is right up here, those 4 ingredients in your model. With these 4 ingredients specified, there's one and only one way to do inference, one and only one way to do prediction, one and only one way to do decision. With these 4 ingredients specified, or I'll put it this way, I won't be so harsh. A method that produces logically internally consistent results is based upon there being only one equation for inference, one equation for prediction, one equation for decision. I won't claim that this is the only method, but a method for yielding logically internally consistent answers is as follows. So, number 1, inference. It proceeds essentially in 2 steps. Step A, write the likelihood function as any positive multiple of that sampling distribution, but viewed as a function of theta for fixed data values for arbitrary positive C. That's our likelihood function. And then step B, compute. Posterior distribution, which is the name people give to this thing here. It should really be called the full information distribution, combining information both internal to the data set and external to it. Posterior distribution equals a constant times the prior information in density form times the likelihood in density form. So there you go. One equation for inference. The problem is solved. And that brings us to why we've been doing all that MCMC stuff last time. This is an equation that says what to do, but these things are densities, and somehow you have to summarize this density. And even if theta is a vector of only length 1, so even if it's just a scalar, this can be not quite as pleasant as you might like, and especially when theta is a vector of length k, where k is some big number, this can be a quite unpleasant thing to try to summarize. It may not have a closed form expression that's very easy to work with. Various summaries of it may well be difficult to extract in closed analytic form. And so the whole idea of our session last time was to focus on a particular method of summarizing posterior distributions via simulation-based methods. That's where Markov chain Monte Carlo came in. So all the stuff we did last week, which was a whole bunch of trees about Markov chains and equilibrium distributions and burn-ins and monitoring runs and all that stuff, that's all just trees in the forest of trying to summarize posterior distributions by simulating from them. Then there's only one equation for prediction, and it goes like this. Future data d star, then your predictive distribution for d star given the data so far and the background is the integral of the predictive distribution given the truth and the data times the posterior for theta given the data d theta, where this integral is over capital theta, which is the set of possible values of the unknown theta. And often, as we've seen before, if you knew what the truth was, the past data values are not helpful to you in predicting the future ones. And so this integral often simplifies to where we can cross through the theta. So I'm just going to go ahead and cross through it in dotted lines. This is not always something that's okay to do. In time series models, sometimes you need to know what the truth is, and you also need to know the past data to predict the future data. And there are other situations where that happens as well. And so generally we are able to cross through that, and both of these are ingredients we know. This is the sampling distribution. No, I'm sorry, I crossed the wrong thing, didn't I? Wow, that was really bad. Whoa, I just, the program just crashed. Theta and D and B, and the thing that I'm allowed to cross through is the D. So this is now just the sampling distribution in disguise, and this is the posterior distribution, which I just worked out how to do in step 1. So prediction is easy. And then finally, of course, that integral might not be any fun to calculate or approximate, and that was the big Achilles heel of this stuff for a long time. The integrals were too hard. And now finally, 3, decision. You simply find the decision A star that maximizes your expected utility function, where the expectation is over the current posterior distribution that carries all the information, maximizes expected utility. And we looked at one simple example of that earlier, and we'll be looking at some more rather more complicated examples of it later on. Okay, so that's the big picture. We start with something we don't know, theta. We start with a data set, capital D, that we hope will be helpful in decreasing our uncertainty about theta. We start with a set, script B, of true-false propositions that quantify the background information. We define conditional probability as an operator on 2 true-false propositions, one of which is given and the other one is uncertain. We generalize that with cumulative distribution functions and densities for things that live continuously. We notice that to get to the finishing line in the Bayesian story, you have to specify 4 things. The thing that we call the prior, the thing that we call the sampling distribution, the thing that we call the action space, the thing we call the utility function. Having specified them, we collect them together into a thing called your model or your uncertainty about theta. And we acknowledge that there's secondary uncertainty. There's primary uncertainty about theta. There's almost always secondary uncertainty about the model that's intended to quantify your uncertainty about theta. So we're going to have to cope with that later on. We've been punting about that so far. And then the payoff is once you've specified these 4 things, there's a single simple to describe method for yielding logically internally consistent answers. One equation for inference after converting the sampling distribution into the likelihood function, one equation for prediction, one equation for decision. Now, if I were a snake oil salesman, you would have heard my pitch for why this is great. And as I mentioned before, whenever someone's trying to sell you something, you should always ask, what's the downside of what you're proposing? And so the next, yes, please. Yes. The formula for computing this expectation is you integrate this utility function over the posterior in theta, and that gets you a number that is specific to that action A, and then you do that for all the different actions, and you find the one that makes that number as big as you can. So we are coping with our uncertainty in theta in probably the simplest way possible. This guy, Frank Ramsey, proved that this is the right way to deal with it. Basically, if you knew what theta was, you'd just maximize utility, because then you just find the A for the true theta that makes things as big as possible. But since you don't know what theta is, Ramsey showed that the simplest possible thing you could do, which is to average this utility over your information about theta, and pick the A star that makes that as big as possible, is the right thing to do. So it does work. So what are the challenges to this paradigm? Well, Roman numeral 1, the specification burden. And I'll have more to say about that in the second half of the class. Roman numeral 2, computation. So, where we were last time, so P of theta given D and B is some constant times the prior times the likelihood. Okay. Suppose theta is that vector of k real numbers that we were talking about before. Then each of these, and the these in question, that guy there, that guy there, that guy there, is a k-dimensional probability distribution. DIST for short. And if k is bigger than 2, maybe 3, we run out of abilities as people who process our world through 3 dimensions. We run out of the ability to even visualize those distributions, much less extract useful information from them in a way that hits you right between the eyes. Immediately people start thinking about doing the thing I mentioned before of that old parable about the blind man and the elephant. You think about saying, well, that's going to be hard to visualize. So each of these is a k-dimensional probability distribution, hard to visualize and work with directly. So why not think about working out the marginal posterior distribution for theta 1, and then do the same thing for theta 2. That'll be a one-dimensional distribution, and you could hope that you learned about the full distribution, a lot about the full distribution, by extracting each of these marginals and then looking at all of them together. So this is called the marginal posterior distribution for just the component theta 1, given D and B, of course. That's the name people give to that thing. But look, to compute it, we have to be prepared to do a big old hairy integral in which we write down the joint posterior distribution over all of them, theta 1, theta 2, dot, 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 down to theta k, given D and B. And we add up or integrate over all the other components, d theta 2 down to d theta k. And so this is a k minus 1 dimensional DIM for short integral. And I bet when you took calculus, there wasn't a very long part of the class in which they told you about how to work with 15-dimensional integrals. You learned about how to work with one-dimensional integrals. You learned a little bit about how to work with two-dimensional integrals, and that's where they stopped, probably, right there. Something that they don't even talk about in calculus, namely imagining and coping with a 100-dimensional integral, is right at the heart of the Bayesian story if you have a 100-dimensional unknown. So that's nasty. Moreover, there would be not just one of these; there'd be k of them, one for each of these individual marginals that you're trying to compute. And so, and there are k of these k minus 1 dimensional integrals. I see that we've reached the moment for our first break, and so let's start again at 10:15, and I will continue writing these things out here during the break. So I'll see you again in a few minutes. And audiovisual guys, if you want to shut things off for 15 minutes, that would be great, and we'll start again at 10:15. Basic question.